Okay, so I'd like to continue to march through what we've been trying to cover in here. Actually, this I can now put away. And the last class I gave, we were talking about mathematical preliminaries, and we talked about probability and a bunch of things. I wanted to talk about two other things before I gave up on what I consider to be preliminaries. And the first is to talk a little bit about what is meant by correlations, because this is kind of a very important, this is a very basic statistical thing that is going to be driving a lot of what we do in here. And we say typically we have some variable or variables x, and we have some target that we're interested in predicting y, and we'd like to try to predict y given the values of x. And the correlation coefficient of two variables measures the degree to which one is, in some sense, a function of the other, and vice versa. Okay, there's not a directionality here that's really implied. Okay, if GDP predicts literacy rate predicts GDP. Okay, and the correlation coefficient is a way of measuring for two variables. We can think of, if we have n observations of two variables, we can think of them as being n pairs, xy pairs. The correlation coefficient is going to be a statistic that's going to range from -1, meaning the values are anti-correlated, to 1, meaning that they are completely dependent upon each other, to 0, meaning they are uncorrelated. Okay, and it's important to have the distinction between these three things in your mind. Any questions? Yes?
What is the difference between anti-correlated and uncorrelated?
Okay, so let's say, what is the difference in anti-correlated and so the uncorrelated means it has no predictive power. Okay, so if I take a look at my guess is your birth weight has nothing to do with your your grade in this class. Okay, if I took you at the end of the semester, I took your GPA on one side. Here we've got birth weight, and here we had your grade average. Maybe again, I don't know what your units is. Let's say that I happened to have been about 5 pounds. I was very light. I was about 5 pounds 1 ounce when I was born. My grade in here would be very, very good since I'm assigning it, right? You could imagine listing all these pairs. Certain pairs of variables presumably have very little to say with it, right? If a variable x has little to say about y, then we would say it is uncorrelated. If things are negatively correlated, it means that the higher your variable x is, the lower your variable y is. So let's say that this was the amount that you smoke, okay? And this was lifespan, okay? The more you smoke, the shorter your lifespan is, right? You don't smoke 0, you live to be 100. You smoke like a chimney, if it's, you live to be 6 or something like that. Does everybody get that idea? That is an inverse correlation, okay? And it's important to see when things are anti-correlated, when one thing going up means the other thing goes down. Now, from a point of view of prediction, which is better? Something being strongly anti-correlated or strongly correlated? Equally. Okay? I know that this guy, I can predict this guy's lifespan perfectly fine given the smoking number, right? Even though it's anti-correlated. Okay, so in this case, the values of correlation near 0 are the ones that are least interesting to us. That's kind of the important property here. Any questions? Yeah.
Uncorrelated meaning they are completely independent of each other?
Well, completely independent. Uncorrelated is a word people use. Okay, if you determine it means that it's very restricted if you insist it's exactly 0. The correlation coefficient be exactly 0. Typically, what I would say is that there's regions where when the correlation is near 0 or near 0, it's not going to be that interesting or that predictive. When it's going to be near 1, it's going to be or near -1, it is going to be, in general, very predictive. Okay, and exactly how much that is what we want to quantify today a little bit. Any questions? Yeah.
So if X can predict Y and Y has the same predictive power over X, and that's what
Yeah.
the correlation tells you, right? So
Yeah.
can we say that the reverse is the same exact correlation coefficient?
Yeah, the correlation coefficient the correlation coefficient of xy is going to be the same as the correlation of yx. So there's no directionality here assumed. That's kind of an important thing to realize. Okay, it's given two of these things. What is what is it? So how do we compute correlation or measure correlation of two streams of numbers? In general, again, with all of these things, we're assuming that we have n xy pairs. Okay, so there's going to be, again, n items. Each of them has an xi and a yi. Okay, and we want to know to what extent are the x's correlated with the y's. That's kind of what we're dealing with. And there's two different measures of correlation we're going to look at here. But the most famous one is one called the Pearson Correlation coefficient. And the Pearson Correlation set basically looks like this, okay? It is saying that it's summing up on the top. Actually, wait, right. Can people see my mouse? Is that here? Okay, so it's a sum of, for all n, of the difference with the x value minus the mean x value times the y value minus the mean y value. Okay? And so if we look at that, and the thing that we're dividing it by here is something related to the square root of the sum of the differences from the mean squared. This thing is sort of like the variance of x, and this thing is sort of like the variance of y. So if you want to read this thing, the way I would read it sort of is that this is the differences from the mean, the sum of the products of the differences from the mean, which is something they call the covariance, divided by the variance of of x times the variance of y. It's something like that. Okay? Any questions? Okay? Now, why does this work to measure similarity? Let's look at what it's really doing. The real question is, we want to know whether the correlation is a measure of how in sync are these two variables. Okay? So if one of them is much bigger than the mean, we want the other one to be much bigger than its mean. Does that kind of make sense? So what this is saying is, if x is bigger than the mean of x, that is a positive number. If y is bigger than the mean of y, that is a positive number. A positive number times a positive number is a positive number, right? So we get points for that, right? If x is less than y, the mean, it is a negative number. If y is less than its mean, it is a negative number. A negative number times a negative number is a positive number, okay? And so we would expect that if they are in sync, okay, both being below the mean or both being above the mean, okay, then they contribute positively to this, right? Now what happens if x of I and y sub I were both randomly drawn? I'd say there's a 50% chance it's above the mean and a 50% chance it's below the mean, right? Half the time they're going to agree, giving us a positive number, and half the time they're going to disagree, giving us a negative number. So we kind of believe that if the variables are not in sync, these positive and negative terms kind of should offset each other. And that is why, in principle, the sum of this thing is going to go to something like 0 if they are uncorrelated. Does everybody see that? Okay? So that is the principle behind what this thing is doing. Okay? And why this formula works. Any questions? Why do we divide it by the variance of these things? That's kind of the magic that it takes to bring it to a nice -1 to +1 scale. Okay? Any questions about that? Okay, yes?
Is it possible to get a high correlation coefficient even if the scatter plot does not look linear?
So the question is, it has to do with scatter plots being linear. I think at some point I'll have scatter plots in here. So here is a scatter plot. Okay, what is a scatter plot? A scatter plot is where you draw a graph where you plot each item by its xy value, right? So each xy value is a point. You can look at a plot of these points. He says, does this have something to do with regression lines, or is there a linear fit? In general, we can use linear regression to find a line through any set of points. But basically, the correlation is going to tell us how good the line is. It's not going to tell us the slope of the line. Okay, the slope turns out to have nothing to do with it. But it is going to be a relationship between the higher the correlation, the closer the points are going to be to the best possible line. Okay? Any questions? Okay, let's go back then. Okay? So what are representative correlations? I looked some up to take a look at it. Again, there's a high correlation between smoking and mortality rate. Okay, 0.7. There is a highly negative correlation between income and coronary heart disease. The more income you have, the less coronary disease you have. Okay? So and in fact, according to these numbers, it would suggest that that effect is a function of, what you call it, something almost as strong as smoking, in fact. Okay, why might that be? Maybe you have access to better food and better medical care. That is probably a lot, that's probably what a lot of that has to do with. A lot less stress in general if you don't have to worry about where your next meal is coming from. Things like this, okay? Correlations between like test scores and GPA was about 0.47, which is a pretty strong correlation, but not ungodly strong. I can't take a look at you and just take a look at your SAT or your GREs and predict how good a student you are. Okay, I can try, but it's not going to be perfect. And in fact, SAT scores correlate roughly as well with how rich you are as as how good you'll be in college. Okay, so these are interesting things. People have studied the correlation between how much video games you play, okay, versus how violent you are. And in this study, they showed a positive correlation, but smaller than what we were looking at here, okay? So you guys are not necessarily terrorists if you play some video games, okay? Any questions about that? And it's important to get an intuition a little bit as to how strong a correlation means something, because in here we're going to be making use of correlations a lot, okay? And, it's important to understand what they mean, okay? Any questions? Yeah?
Does it sometimes make sense to calculate correlation between more than two variables?
The question is, does it make sense to correlate between more than two variables? The correlation coefficient as defined is going to be just between two variables. What it makes sense to do for a lot of projects, if you have more variables, is to compute the pairwise correlation between each pair of variables. Okay? So if I had a big, a data set that I was trying to get a handle on, a terrific thing is to look at the pairwise correlation between every pair of variables. If I see a correlation that's extremely high, maybe that's very interesting for prediction. Or maybe it means it's redundant. Suppose in my data set I had for everybody's height in feet and everybody's height in meters. That would be perfectly correlated, right? And the result would be that one of them is probably, if you have one, you don't need the other, right? So yeah, so having the matrix of correlations is a terrific thing to have is for inspecting your data set early on, yeah. Is that going to what? Well, right now we haven't been talking about, I haven't talked about type 1 error yet or something like that. But again, that has to do with whether, when you make a model, whether we're going to count false positives as being, sometimes we're going to make false positives, predicting something that isn't true. And sometimes they're going to be false negatives, okay? And, so we will talk about these kind of errors later. What is true is that, that when you're building models, you have to be careful about what you're doing when you have very highly correlated variables. Because in principle, if they're very highly correlated input variables, both probably doesn't contribute more than one of them does. Okay? And thinking about that is something you got to be careful of. Yes?
Is correlation transitive? If X can predict Y and Y can predict Z, can X predict Z as well? Can I substantially say that? Or do I have a coefficient for both of them?
To be honest with you, I don't know any result like that. Okay? My instinct would be that it's probably true. Well, let's think about it. If I am correlated, X is correlated with Y, and Y is correlated with Z, is X going to be correlated with Z? My guess would be likely yes. But of course, these correlations, these transitivity things, these are numerical relations. If X is correlated with Y 0.8, and Y is correlated with Z 0.7, what is the correlation between X and Z? Well, you can't directly compute it, okay? It measures in some sense how in sync they are. You probably could compute some kind of bounds on it. But even that, I'm not familiar with results like that.
I could give you a counterexample. If you keep smoking, your lifespan goes down.
Yeah.
You would have another pair, like how much your lifespan and your sleep. If you sleep less, you live less. But then smoking and sleeping are not really correlated with each other.
Okay, so exactly what the transitivity of these things are depends upon what it's okay. So as far as transitivity, I don't know of results that prove it. In general, you would like to think that there is usually some level of transitivity here, a little bit, but it's not clear that there always is. Okay, and you can probably prove something about the minimal amount of transitivity that's possible. Okay, but but anyway, so that's that. Any questions?
Sir?
Yeah.
The correlation may not always imply causation. So if we are do just give the example that if you have high income, then you have low coronary disease. Like, so how did you imply that because of this factor it was caused? Like,
okay, so as we will say later on, correlation does not imply causation. Okay, now on the other hand, correlation often suggests things, and I have no doubt in my mind when I see this that there is a relationship between income and mortality due to coronary diseases. Both these things have been measured. They've probably with large enough data sets that you can talk about how significant it is. That's going to be my next thing. And I see a mechanism by which they are probably meaningful. So I have to me, it's one of these correlations that makes sense to me. Okay? I'm surprised a little bit about how strong it is, but it's not a completely crazy correlation.
okay, so if it makes some sense and it has some high value, then you will say that it implies causation.
Well, okay, no, saying something implies causation is a very, very difficult question. Okay, we're not going to in here generally say anything about causation. We're going to be using models to try to predict something. That's generally the level on which we are working here. And so we're going to try to build if I want to try to build a model of whether or not you're likely, you come into the hospital, your chest is hurting. Are you likely to survive? Okay, it's perfectly reasonable for the hospital to want a model for this. And if putting the variable of what you have in your bank account helps make a good prediction, then that would probably be a good thing to do. It's not completely a causation thing, right? I don't have to make any strong claims about causation there, okay? But on the other hand, there is a need for a sniff test a little bit. When you build these models, if you're building things from variables that obviously make no sense, you should be suspicious, okay? There's a famous example, if any of you Google the word butter production in Bangladesh, okay? There was a famous example where somebody was trying to predict whether the stock was going to go up, market was going to go up or down that year. and they correlated it against a large number of variables in on some UN data set. And the best correlation by far was stock market, U.S. stock market against butter production in Bangladesh. They had great results from this, okay, up until the moment they published it. And then years after it didn't, okay? And, you shouldn't be surprised if that model fails, okay? Because, it doesn't make any sense that there's a correlation, okay? To a certain, remember, when we're building models, we are trying to be wise people and use wisdom. And part of wisdom is trying to figure out, does something make sense or does something not make sense? Any questions? Yeah. Okay, so this is a question of how many, you want to know how many pairs of points do you need for a correlation to be interesting. Now let's talk about two things about interpreting correlations. That's what we're going to get to on the next slide. Okay, the slide after this, I think. Which is a question of how many observations make a correlation interesting. Okay, so I'm going to claim there's two different issues in interpreting correlations that we have to be aware of. The first is to what extent a correlation should explain a variable. And there's a statistic basically called the correlation squared. The square of the correlation, okay, estimates the fraction of the variance of variable y that would be explained by variable x in a simple linear regression. So often when you talk to someone about a variable, they'll talk about, oh, what's the R-squared score? And what they're trying to figure out is how much of y is explained by this correlation, right? Suppose, let's say, we took a look back at our correlation of, let's take a look at this thing. For smoking, okay, what's R squared? R is 0.7. What is R squared? It's about 0.5. That would say that about half of the variation in mortality is explained by smoking, which is pretty strong, right? What is the amount of violent behavior that is explained by video games? What's 0.2 squared? 0.04. That would argue that something like about 4, using this as, be it a heuristic or whatever, that's an argument that 4% of the variance might be explained by the video game thing, right? So if you're trying to predict violent behavior, if you're trying to pinpoint a terrorist, probably starting with the video games is the wrong variable to be looking at, right? Even though there's a strong correlation there, a reasonable correlation, yeah. Why do we square it? Okay. So what I would say is, I'm not going to quite say why, but I am going to say what it means when we say the fraction of variance explained goes according to R squared. This is kind of what does that mean? Okay? Generally speaking, the following. Here we had one of these scatter plots, right? This is a set of points on the XY scale. And as we see, there is a nice linear fit here. Does everybody agree? And there is, in fact, I think the correlation here was, I think here, 0.94. This is a very good correlation, 0.94, right? Now, what is the variance of the value of y? Okay? If you look at it, the values of y go from down to minus 0.5, it looks like, all the way up to 0.6, right? So the variance here is, even though these things are, even though these things are fit nicely by a line, the variance here is going to be a number. The variance of the y values is a number. And these numbers range roughly, I'll say, uniformly over that interval, right? Now, suppose we subtract off, we use x as a predictor. We come up with a regression line, a predictor. We'll talk more about regression lines later. But we came up with the best fitting line that describes those points, right? That's what this line here is. Suppose now we replace the values of y by y minus f of x, our prediction, right? So this point is now going to be, the value is going to be this minus, come back here. This minus this. For this point, the value is going to be changed from this to this minus this. Does everybody see that on this side here, I am now plotting, instead of y minus f of x. Okay? Now what should be clear? Which do we think is going to have a smaller variance? The values of y themselves, or y minus the predictions, which we call the residuals? Which values do we think will have smaller variance? Does everybody see that these values range from minus 0.2 to 0.4 to plus 0.2, right? These vary over a much smaller range, right? When we square this thing, there's the relationship that 1 minus the square of r is going to be equal to the variance of the residuals over the variance of the y's. This is why the r squared comes from, or why people talk about it. It's kind of an explanation of how much of the variance, okay, in this set is explained by that variable, right? What if there was a perfect correlation? What if y and x were perfectly correlated? What would those points look like in this image? They'd all look like on the line, right? So we would expect, if the points were all like that, this is the best fitting line. This would be the best fitting line. What would the residuals look like? They would all be 0. Does everybody see that? And in that case, all the variance. What's the variance of n values, all of which are 0? Okay. So what this is kind of saying that's good is, this is a way to think about how much explanatory power a correlation has for predictive purposes. Does everybody kind of get that idea? Any questions about this? Okay, yeah.
Is there any threshold value to compare the values of R square so that we reject it between the two variables?
Okay, so I think what you guys are now wanting to know, I'm kind of proud of explaining this, which is this idea of that there's this notion of how much does a variable explain. There's two different issues that we have. One is how much does the variable explain, and the other is how much do we trust the correlation. Does everybody see that there's two different issues that we have here? Okay, I think that you were asking me how much do I trust the correlation, right? Why should I have been suspicious about butter production in Bangladesh, right? Versus, wow, there's a great correlation with butter production in Bangladesh. How good a model can I now build for the other one? This R squared issue is getting at how good a model can we build if the correlation is the right, if this correlation is the right correlation. Okay? Any question? Okay? Okay, so does everybody see kind of why the R squared comes in? And why, once, it kind of makes sense, it's kind of, if we really have a great fitting line, then we're really explaining almost all the variance, right? On the other hand, what would you expect to happen if you had a completely random set of points? Could you fit a regression line through this? The answer is yes. Would it be a good regression line? No. Okay, now what's the regression line? Perfect. Okay? Now I measure the residuals to this. Would we expect the residuals to have gotten smaller? Then, think about it. The values of the residuals compared to the values of y? Not really. Okay? So in that case, the R value would be 0, and we would expect to have explained nothing, right? And, the fact that it's an R squared thing falls out of analysis we're not going to do here, okay? But again, this is why R squared is a meaningful statement. It's not just that they decided they like squares better non-linear terms. Okay? Any questions? Any questions about this issue of how good does the explanation is the explanation? The next issue, that was what you guys really wanted to know, it seems, is how interesting is a correlation before it becomes significant? Okay? And again, we will talk more about statistical significance in here later on, but it's important to understand that there is this kind of an issue. It's easy to take a small number of points, find there is a high correlation, and overgeneralize this as being, wow, I had 10 points here and I got a correlation of 0.3. Okay? Is that good? Is that bad? Is it meaningful? Okay? So there's this notion of statistical significance. And when you read scientific papers, there is this notion that usually people talk about is a claim, okay, statistically significant to a certain level. Okay, and typically what people use, often people use a number of 0.05, which means something is significant if its chances of the odds of it occurring by chance was 1 in 20. That's kind of it. If it's a 0.05, that kind of works out to 1 in 20. Okay, and a common convention in scientific papers is something is interesting if the odds of it happening by chance was less than 1 out of 20. Okay? So if we take a look at it, we could imagine a curve where suppose we took two random, x value and random permutations of a y value, and we compute the Pearson correlation. We can ask ourselves, what's the likelihood that we would get if we had it on 10 items, what's the likelihood we would get a correlation of a particular value by chance? This gets into those permutation tests that we were talking about, right? And when you use methods like that, there's a curve you can define between, for a given significance level, here the odds that it happens is this high, more than 1 out of 20 times by chance, okay? As a function of the sample size. The larger the sample size is, the less likely it is that a particular correlation value will occur by chance. Does everybody kind of see it? So if you have a very, very small number of points, let's say on this graph it looks like 25 points, there is a 1 in 20 chance that you would observe a correlation of about 0.35. That's the way I read that table, right? So if I have 20 points and I get a correlation of 0.35, should I be really excited about it? Not really. But this line is kind of the boundary between whether you should start to believe it's interesting or not. Does everybody agree with that? And what do we observe? As n gets very, very large, the bound for a correlation to be interesting drops, right? So let's take a look at that. It looks like on this thing, if I have 250 points, and I have a correlation of 0.15, okay? What is the likelihood that it will be by chance? That good? About less than or equal to 1 in 20, right? So quite possibly, that's a real phenomena. You've discovered a correlation of about 0.15, like the video game versus, you could imagine now if we had 25, the correlation was, let's say we took that video game one, right? Maybe they had 250 video game people, right? They, they have them watch video, can measure how much they watch video games and how much they hit people, right? And they correlate that, and that correlation came out to by 0.19 when I remember it, right? If that is above that is over here, we would say that is probably significant, and that is an observation that probably didn't happen by chance. Okay? Any questions? Okay? So it's important to think in terms of these significance. When you present a correlation, to know whether we trust your correlation, we need to have a value of what its statistical significance is. Yes?
So this curve is separating what is relevant and what is irrelevant in terms of correlation.
You say relevant. I think I'm going to say what is real and what is non-real. Okay? That's kind of, I guess, the way that I would like to put it. When you compute a correlation between any two things, you get a number. Is that number right? Well, that number is the correlation of those two particular data streams. So yes, that's a right number. It's a question of whether or not we should trust that this higher correlation didn't happen by chance.
But if we go like the other way around, so that would mean like for small sample sizes, we can just have a very strong correlation out of nothing. I mean, all the time, that is what it means, right?
Right, so what this tells me is, if I took 5 of you in the class, okay, and I measure the length of your hair and I correlate it to your GPA, and I see a perfect correlation, should I recommend to my students that they not visit a barber? The answer is no. Okay, that was a spurious correlation. Okay, the odds that it was one correlation. If I sorted the students by hair length, maybe they would sort them by GPA. They came out in the same order. If I felt that that was representative of the whole population and that was a phenomena that would always come true or be likely to come true, then yes, I would say don't go to the barber. Okay? But what this is telling me is I shouldn't place too much weight on correlations from small numbers of samples. Okay? Do you kind of agree with that? Any?
Yeah, in cases like where you have like surveys, so there will always be some data which will be very close together, right? I mean, that sort of a scene, like, let's say you are measuring like any example like medical, any data like coronary disease. So like some data will always come from a particular hospital, right? So that way
Okay, there's differences between, recognize that there's a difference phenomena, one you might argue is bias. Okay? So suppose, let's say I have a data set of, I put together a data set of, let's say, hair length and GPA. And I give you a list of 10,000 people, okay, where the hair length and GPA correlate 0.99. Wow, that would be a really strong correlation. That's very unlikely to happen by chance, right? But what are the chances that I was lying through my teeth and I made the numbers up instead of actually measuring them? Do you see that that isn't being captured in here? Okay? So that's a somewhat different phenomena of whether I'm lying or cheating or there's a bias because I'm only doing it among people who are bald or some kind of a sampling thing. What? Or a military school or something like this. Okay? So recognize that bias is a different phenomena that is an important thing. Okay? Yes?
So as the sample size increases, the coefficient decreases, right? And
Yeah.
so where do I fit in how does the p-value fit into this if you explain that again?
Well, the p-value here, this line is drawn for 0.05. Okay? This says, what is the likelihood? The likelihood that with this sample size, by chance, I would get a correlation of this big was 1 out of 20. That's exactly what this line is. I could imagine a separate curve for a lower p-value of 0.01. That curve would presumably be shifted up here, right? I would need higher levels of correlation to trust it more, right? Okay? Any questions? But notice, any questions about it? So it should be clear that the larger my sample size is, the smaller correlation I need for it to be unlikely to have happened by chance. Yeah.
So we're saying that the chance of a 0.05 strength correlation occurring in a sample size of like 50 is 0.3?
Yes.
That's what we're saying. Okay.
That's basically what we're saying. Right.
So we're measuring correlation of correlation.
No, so what we're measuring here, that's not what we're measuring. We're measuring that if I took random x and y's, okay, from, or random permutations of one of these things, okay, that if I had 50 points, almost 1.3 of them would show almost 1 in 20 of them. Actually, let me be precise here. What this point is saying is that if I took permutations of 50 points, okay, almost 1 in 20 of them would show a correlation of about 0.27 or greater. Does everybody see that? So it's showing that this is a level that is rare but not ridiculous to happen by chance. That's really kind of what I would say, right? So this says that for this many points, what is the level of correlation that is rare but not ridiculous to happen by chance? Okay? Any questions? Okay, and if you have a different notion of what rare is, like 0.01, you would define a different curve here. Any questions? Okay. One way to interpret it, though, just make sure that we understand what this means. It looks like as you get larger and larger sets, values of n, it takes a smaller and smaller correlation for it to be unlikely to have happened by chance. Does everybody agree with that? For a particular p-value, okay, like 1 in 20, okay, it should be clear that it's that as n gets larger, a weaker correlation suffices for it to be unlikely to happen by chance, right? Now my question is, does a weak correlation explain very much variance? Let's think about these two different things here. Right? There is a question of, if we have a large data set here, a small positive correlation may be unlikely to happen by chance, right? But even if it does occur it did not occur by chance, does it explain very much? Okay? The thing I want people to yell is no, and I'm seeing puzzled looks here. But if we combine this observation with the previous one, does everybody see that the R squared measures how much explanatory power is there of a, of a correlation? The significance level measures how likely is it we would have gotten this by chance. Does everybody see that? And these are two different things, okay? If I did my violence in video game study on a large number of people, and I got a correlation of 0.19, it's very unlikely that happened by chance. If I did my study honestly, that probably suggests there is a connection, right? But because of the R squared value, 0.19 doesn't explain very much, okay? So does everybody get this distinction between significance is unlikely to be by chance, and R squared is explanatory significance, assuming that the correlation is real? Okay? Any questions? Okay?
Sir?
Yeah.
If we vary alpha equal to 0.05 of other values, then how is graph change?
So recognize that, again, if we have a smaller level, smaller is usually tougher standards. If it was 0.01, we would expect the curve to shift up here. We need a higher correlation for each size in order to be impressed by it, right? What's the likelihood there was a 1 in 100, a correlation that occurred 1 out of 100 times? Might have been at 0.5 instead of 0.3, right? Which was would occur less than that. Okay? Any questions? Yeah. Why is it growing down? Well, this is the horizon between something interesting and something uninteresting. Okay? And a correlation gets interesting if you show it with a large number of people. You're more likely, you need a weak, you can be convinced that a weak correlation is likely a real correlation. Okay? Even if it doesn't explain very much of it. Okay? Any questions about that? Yeah.
So with a very high sample size, it is easier to prove something is significant, but it might not tell you very much, right? That is what we're trying to
Right, that's exactly what I'm saying. That for a large sample size, it's easier to prove something is significant, but it may not explain very much. Okay? So this is one of the great things about big data if you're a researcher. You get lots and lots of examples. You can prove the significance of something that's provocative sounding, but probably isn't that important. Okay? Does hair length correlate with GPA? Okay? It would not surprise me if there is a relationship between this, right? If you're a male, you have a long hair, maybe you're kind of a crazy guy and you don't study as much. Okay, the people with short hair in the military, they have more discipline, right? It would not surprise me if there was a correlation there that was non-zero, and that if you took a look at enough people, you could prove it, and you could probably say that even if there was a 0.01 correlation, if you had enough heads that you had examined, you would be able to say, look, this is a real phenomena. Hair length makes a difference. But does it make a real big difference? The answer is no if the R squared is small. Okay? That's kind of the trade-off that we have. Any questions here? Ideally, we want our R squared to be high and our sample size to be high, and that our significance level is very, very low. Any questions? Okay. So, anyway, again, when people do big data things, it's often the case that they're kind of, if you have a lot of variables on a data set, typically if you want to build a really complicated model, you might have a lot of variables, each of which explains only a small effect. Your hope is maybe you can explain the whole thing or a large part of the variance by using a large number of variables, maybe all of which are kind of weak. Okay? That's kind of the hope anyway. Any questions? Yeah.
If you think of it in non-mathematical terms, so should this significance not depend on the nature of the problem as well, the sample size that we are taking? So, for example, for some problems, a large sample size might be needed to understand that the correlation that we are getting is indeed believable. For some problems, we might have this confusion with a small sample size.
Okay, what I would think is an extraordinary claim requires extraordinary evidence. Okay, is in general true. So, so it is probably the case that if you're making a claim that is extremely surprising, like the butter production in Bangladesh thing, okay, I would probably need a higher level of significance before I believed it than if you told me that, the interest rate, okay, that year correlated with the price of the stock market, right? But in principle, this idea of statistical significance is supposed to wash these issues away. You know that if it doesn't rise to this level of significance, you can discard the observation. Okay, and it gives you a way to test whether the butter production in Bangladesh, how meaningful is that, or any other correlation. Any questions? Okay. Okay, there are other ways of measuring correlation that are interesting. And there's one other one which I'd like to mention called the Spearman rank correlation, which is the Pearson correlation is basically driven by how well something fits a line. Okay? If you take a look, though, at this example, let's look at this set of points. Here, this is the x value, this is the y value. Okay? From this data set, if you look at it, there is no good straight line that fits those points. Does everybody kind of agree? But if I gave you a value of x, could you predict the value of y accurately from those points? The answer should be yes. In this case, it happens to be that if x is less than 5, fit it on this line, and if x is greater than 5, fit it on that line. You can come up with a perfect model for it. Does everybody see that? So the Pearson correlation measures how good a linear fit there is. But sometimes there are other relationships that are not linear that can be better picked up by other statistics. Okay? And the Spearman correlation coefficient is a good example of something like that. Okay? What it's going to do is count the number of disordered pairs. How often is it that if x is greater, if we have 2 points here, let's take a look at this. We have 2 points. How often is it that if x, you can imagine two, well, okay, what am I going to say here? If we have a linear fit, let's say that there is a nice linear fit here. If I take 2 points at random, if this is x1, if x2 is greater than x1, what do we expect y2 to be relative to x1? Right? That if x1 is less than y, if x1 is less than x2, y1 is going to be less than y2. That's kind of captured by this notion. If there's a good linear fit, we would expect that, right? What the Spearman is going to measure is how many of the pairs of points satisfy that kind of relationship. Does everybody see that on this particular example here? Whenever x1 is less than x2, y1 is less than y2, right? So the Spearman correlation is 1 because that's always true, whereas the linear fit correlation is good but not great. Does everybody see that? Yeah. What if I have one that's like this? Okay, so that's interesting. If I have a set of points like this, this should score a lousy Spearman correlation. Okay, because although not incredibly lousy.
Won't it be 0 then?
Will it be 0? Not exactly. There's a lot of pairs here. There's, you know, if you think about how many pairs there are, there's a lot of pairs defined by these.
Right.
So anyway, so it's a little hard to tell what that is. But so that would be one that you're right is predictable, but might not score as well by this as we might like, right? So that's a little bit pathological. Okay? But it should be clear that in principle the Spearman rank can capture things that are can show value to certain things that the Pearson correlation wouldn't do. Okay? Any questions? It's also the case that that the Pearson correlation can be less sensitive to outliers. Okay, if we look at this particular example, this is an example of points where the Pearson and the Spearman correlation are both 0.94, right? So this is good. But if I took one of those points and lifted it all the way up, see what I did here? I jacked that up. This is going to now cause a big shift in the regression line as it tries to go through and get something from that distant point, right? And that's going to mess up the linear relationship of a lot of points. But for the Spearman correlation, it doesn't make much difference. The only real difference is that these points on the end are less happy than they were before, right? So the Pearson correlation can be better with nonlinear relationships. The Spearman one can be better with nonlinear relationships and outliers. Any questions about that? Okay, so how do you compute it? Again, what it amounts to is that there's the following kind of formulas computes it, where what we say is for a particular value of x, for the ith point, the distance for the ith point is, okay, let's go through it like this. The rank of a x sub I among the x's is where x sub I would be in sorted order, right? If x sub I is the minimum value of all the x's, then x sub I, rank of x sub I would be 1. And if it was the maximum of all the x sub i's, its value would be n. Does everybody get that idea? The deviation, let's call it, of the ith value is the difference between the rank of its x value and its rank of its y value, right? If it's sort of well-behaved according to permutation, they should have the same number of guys underneath it and the same number of guys above it among the x and the y's, right? So what the Spearman correlation, it turns out, is the sum of the squares of these deviations divided by a term that is going to normalize it. So the thing comes out between -1 and 1. Okay? Turns out the sum of the squares, in the worst case, you can imagine 1 through n to n through 1. That would be the worst case for the Pearson correlation. And you can count that the number of out-of-order pairs is going to be basically this. Okay? So, any questions about that? Okay. And another way to think about the Spearman correlation is that it's the Pearson correlation on the rank values. That's kind of where it comes from. So I replace the actual values by their ranks from 1 to n. This is kind of what you get. Any questions? So when you have two variables, you can compute the Pearson correlation, you can compute the Spearman correlation. They're a measure of how in sync they are. Any questions? Okay. Now, as we said before, and we will say again and again and again, correlation does not imply causation. This is a big thing that we want to take a look at. Correlation measures how in sync two variables are. They might be spurious. It might be that one variable x causes y. It might be that variable y causes x. It might be that neither of them cause anything, but they're just basically the same. Okay? And, there's all kinds of, funny things you can talk about if you assume correlation is what you call same as causation. So, for example, we know that the number of police in that are assigned to serve in a neighborhood correlates strongly with how much crime there is in that neighborhood. Does everybody agree with that? Now, do we believe that the police cause crime? Okay, generally speaking, I will say no. Do we believe that crime causes police? Probably. I think to a large extent that might very well be true. Here there is a one-way relationship. Okay? Does your height in meters cause your height in feet? Does your height in feet cause the height in meters? So then there is if you believe that. So trying to ascribe whether something causes something is a very dicey thing. Okay? We're not going to do it too much in here. People in the social sciences worry a lot about this kind of thing, right? And they require actually fairly strong evidence to try to reason that there's really a causative relationship. So correlations are often suggestive of a causative relationship. But there's not really good ways necessarily to tease out that one really causes. There's no generic statistical tools that I would trust to say that one causes the other. Any questions? Okay. So don't get fooled with this when you're building your models, because a lot of people do. Any questions? Okay, boom. I want to go through this quickly, although this is an interesting thing, just because I'm going through this more slowly than I'd like. One special use of correlation that I want you to file away in your head is this idea of autocorrelation. Sometimes you have a set of variables, typically by time series, and you will see that there are cycles inherent in the time periods that affect things. Okay, so for example, here's a figure I found of time series of the number of passengers that flew between two places as a function of time. What do we notice about this time series?
Towards the end of the year, more people fly.
Presumably towards the end of the year, people fly. Okay, but the rest of the year, people don't, right? Or that there is an annual periodicity. You can expect that every December something is going to happen, right? If I want to predict the sales, let's put it this way. If I'm in a store and I want to use past sales data to predict how many sales I will have today, should I use yesterday's sales as a good proxy for how many sales I'm going to get today? Maybe it'll help, but why wouldn't that necessarily be that great? Well, during the week, they're weekends, right? Would the sales a week ago probably be a better proxy for sales today than it would be? I think the answer is probably yes, right? Would the sales a year ago be a good proxy? Let's say I'm selling swimming suits, okay? I probably get very few sales in the winter, but a lot in the summer. So there's some of these periodicities that exist in data that you want to try to identify. How might we be able to identify periodicities in a data? Okay? How, if we had sales data, could we discover the concept of that there are weeks? You know, you're a Martian. You get a time series of sales data. How could you discover that people on this planet had a 7-day week? How could you do it?
Just we can subtract the time series with a trend. Time series can be modeled into trend, seasonal component, and noise.
Well, you want to model it as trends, but how could we do that? How could we tell that? I want to claim that if we took our time series here of today, here's the day X, and I correlate it to the series. Here's the time series, this is X minus 7, okay? Or let's say X plus 7, I guess this is it, right? Does everybody agree that if there was a weekly situation with these things, we would expect a high correlation between sales today and sales 7 days from now over the whole thing? Does everybody get that idea? And if we did this for X equals 6, it wouldn't be as strong. And if we did it for X equals 365, maybe it would be stronger than it would be, you know, if we had done it for X equals 240, right? So you can imagine by an autocorrelation is a correlation with itself. And if you want to detect periodicities in data, okay, it's really a function of if you computed the correlation with a lag of a series with a lag of k periods. If that correlation is unusually high, that probably means that there is a periodicity there. Does everybody get that idea? So this is something you have to do from time to time. I don't want to go into too much detail here, okay? But bottom line is, you know, you often want to compute autocorrelations. Any questions? Okay. The last bit of preliminary stuff that I wanted to do is I wanted to quickly go through what a logarithm is. Okay? Now everybody here should have at one point seen what a logarithm is. This hopefully isn't something that is completely new to everybody. But we're going to use logarithms in here for a couple of reasons that people may not be used to seeing. So what is a logarithm? A logarithm is, by definition, the inverse exponential function. When we say that y is equal to log base b of x, that is just another way of writing b to the y is equal to x. The logarithm is the power that you raise b to get x. Okay? And these, you have to know these equations, and that's the definition of what a logarithm is. Any questions? But what do logarithms mean, and why are we going to use them in here? Okay, it's different than why we use. I give a same lecture. You have to know what a logarithm is when I teach my algorithms class. But the reasons are different in here. One reason we're going to be using logarithms in here is fairly often in evaluating evidence, we're going to be multiplying large chains of probabilities. Suppose I multiply a large number of probabilities. If this is a probability, what is its number? What is the value that we know about that number? It's between 0 and 1, right? And if I have so it's a small number. Does everybody agree with it? And when you multiply a probability by a probability, do you get a bigger number or a smaller number? So if I multiply a long chain of probabilities, I get a very, very tiny number. Does everybody see that? And when it comes to precisions of numerical and how computers work when you multiply large chains of small numbers, they go to 0. They blink out at some point, and that's a bad thing. Now, it turns out that the product of a bunch of probabilities, okay, is the same as b to some power p, to some value p, where p is the sum of the logarithms. So let me come back here. So there is an equivalence. Come back. There is an equivalence between multiplying numbers and summing up their logarithms, okay, for purposes of comparing numbers, probabilities, and things like that. So bear in mind that summing up the logs of probabilities is analogous to multiplying them, but one is numerically a much better thing to do. Any questions about it? That's one reason why we will care about logarithms. Another reason we're going to care about logarithms is that ratios, I told you before when we talked about geometric means, okay, that working with ratios, people tend to do dumb things, okay? And often in here, you're going to want to have features that might represent ratios. What was today's value compared to yesterday's value? Okay? That is a ratio, right? And we had this phenomena that when you do this thing, if you have new price over old price, the value there, assuming both are positive numbers, can range between 0 and infinity, where unchanged means the ratio is 1, right? So there's a lot more room on one side than the other. If you take the log of a ratio, a twofold change upward is going to have the same magnitude as a twofold change downward. Okay, this is an important thing to see here. Okay? So if you're doing something with ratios, often it is better, where ratios are comparing things. A great thing to do is to take the logarithm of the ratios. And that way you get a better idea of whether it's an upfold increase or a downfold thing. Any questions? Okay. On the left is a diseased plot that I once got from some students, okay, where they were showing me for a bunch of, each row represents a circuit, let's say, or a point in a network. And each point represents happens to represent a time period. And it's comparing old algorithm versus new algorithm, okay, or something like that, okay? And they gave me this plot on the left, where this is a ratio of old versus new, right? You see kind of what we're doing? This is a plot where for each one of these I'm plotting a bunch of ratios. Does everybody see it? It's like four series of sets of ratios, right? Which is the outlier among the ratios? Which is the really outlier among the ratios? Looks like this one. That's bad, right? And that's an illusion. The reason is because there's a lot more room here on this side to get big than on this side to get small. Does everybody see that? Here I take this same data and I plot the log of the ratios. Okay, now being centered around 0 is 1, right? Centered around the log of being 0 is the ratio 1, right? This big outlier was this point, right? Where was the outlier among the ratios? These guys are unbelievably small, right? Does everybody see that? If you ever plot ratios, and many of you do, if you don't take the logarithm of it, or plot it on a logarithmic scale at least, okay? It is hopeless here, because you see where all these points, there's no difference if I plot x over old over new versus new over old. It shouldn't look that much different, right? Everybody see you hit it with a log, everything works out nicely. Any questions? So if you ever see a world where your points look like this, you hit it with a log. Ratios. Any questions? Okay. We're going to be talking in here about different kinds of variables in the next, over the next couple of weeks. Things that are normally distributed, things that are power law distributed. When you have power laws, okay, which arise in many things, you tend to get very, very large, a very small number of very, very large values. Wealth is power law distributed in this country. The mean wealth is quite different than the median wealth, right? Bill Gates makes everybody, on average, $250 richer in the United States. Okay? In the mean, but not in the median, right? Now, when you're dealing with a variable that is power law distributed, like wealth, usually it makes sense to, instead of building a model on the power law, on the value there, to build it on the log of that variable. Okay? Why is that? Try to think that, let's say you're going to try to predict something on the basis of wealth. What might be something we're going to predict on the basis of wealth? Let's say lifespan. Does everybody agree with that? You could imagine predicting here's lifespan, here's wealth. Okay? And you could build presumably some kind of linear relationship there, right? How long will Bill Gates live according to that model? Forever. Okay, does everybody see that? And that doesn't make any sense whatsoever. Okay? I have no doubt Bill Gates has access to better doctors than me and stuff like that. What's interesting is if you take the log of these things, you can get a much more meaningful thing. I know I'm going through this kind of fast, but do people kind of get that idea, or is there any questions about that? For things that are not normally distributed, hitting it with a log usually yields a more meaningful thing. For example, when you look at wealth, I think that if we take the log of wealth, I am about as far from Bill Gates as I am from you guys. Okay? And, that's now a more meaningful, thing. If we need to go hire a doctor or do something like that, I'll probably be more successful, but Bill Gates would be that many times more successful than me. Any questions? Okay, yes? I'm not that rich, because logs, what's great about it is you guys are really poor, okay? But the important thing here is that when you do logs, remember, every time you add 1 to the logarithm, you double it. Or if it's a base 10 thing, you multiply it by 10. Okay? If someone is worth, let's say, $1 million, how many logs is it till they become worth $1 billion? Only 3.